Hello, everyone. I hope you're all feeling fantastic. We're going to be looking at question 22 on our 2018 Cayley paper. What have we got for question 22? If n is a positive integer, the symbol n factorial, which they say red n factorial, which, to be honest, in grade 10, it's up in the air whether or not you've seen this before. If you've done some math enrichment, outside of the regular school program, you've likely seen factorials, possibly even something like choose notation for different counting problems. But, if you're I'm a smart kid in the regular school system, this might be something relatively new to you. In which case, if it is and you're sitting there practicing, I would strongly suggest you look up things like factorials, permutations, combinations. Counting problems are not really emphasized a whole lot in high school anymore, but they can be very helpful in terms of doing well on contests. Not just on a Cayley, but on, eventual things like a Euclid or a Hypatia, stuff like that. A counting argument, they're perfectly acceptable, even if it's not a high school level thing or something in the regular high school curriculum, and it can certainly save time. Okay? So getting back to it with factorials, this represents the product of the integers from 1 to n. For example, 4 factorial is 1 times 2 times 3 all the way up to times 4, and that happens to be 24. 5 factorial is 120. 6 factorial, well, you multiply the 5 factorial by 6, and you'll get 720. Anyway, if x and y are integers, so that and 30 factorial over 36 to the x and 25 to the power y is equal to an integer, what is the maximum possible value of x plus y? Okay, so to make x plus y as big as possible, I'm thinking we should make x and y as big as possible. Now, when we look at this, so if this is to be an integer, then 30 factorial needs x factors of 36 at least, and y factors of 25. It may happen that something like 36 to the 10 divides 30 factorial, but 25 to the y divide 25 to the 6 divides 30 factorial. And so we would just take x as 10 and y as 6. We want the most factors of x and y. So we're just going to say, well, how many 36s do go into 30 factorial and that sort of a thing. Okay. Now, 36 is not power of a prime. I guess we could... I would focus on primes. I've seen 2x because it's a square. I'll break this up into a step. So first of all, 36 is 6 squared, so we get 6 to the 2x rather than 36 to the x. Same thing with the 5 to the 2y. But the 6 can be broken down into primes, and primes and factorials are very, very easy to count. Okay. Now, when it comes to making 6s, you need 2s and 3s. There are going to be less 3s than there are 2s, just because, well, what is 30 factorial? It's 30 times 29 times 28, all the way down to times 4 times 3 times 2 times 1. So if I want to make 2 to the 2x, if 2 goes into 30 factorial 2x times, there's going to be a lot of 2's here. Basically, every other number gives you 2's, whereas only every third number gives you a 3, a factor of 3. So the limiting thing here is the 3's. So we need to count factors of 3, and that'll figure out x. And then to figure out y, we need to count factors of 5. Okay, now if you don't believe me, you can do the question and count factors of 2. There will be more factors of 2 than there are factors of 3 in general, but if we need to make a 6, we need to be able to pair them up. 1, 2 for every 3. So a 2 for every 3. But if there's less 3's, then you're going to run out of 3's before you run out of 2's, is sort of what I'm thinking. All right. So, when it comes to counting powers of primes with factorials. So P goes, let's not say goes into, if I've got P as a prime and PK divides 30 factorial, then we can find, I remember this was taught to me by an enrichment program that I went to when I was in about grade 8 or grade 9. So I don't feel too bad using this sort of thing. And if you can learn this, then this is a fantastic thing to know going forward. Because dividing factorials pops up every once in a while. We can find the largest k for a given prime p by counting. So we've got 30, 29, 28. Actually, I think I might even be able to fit these together in a line, just so I can really show off the process. But then we're going to sort of exploit it, and I'll even generalize it so you can write it down if you've never seen something like this before. But as you can see, factorials now have to be defined. I don't think they used to. I think they were more part of the curriculum, but they've sort of fallen out of favor. Counting arguments in general, I think you can still find them in sort of a grade 12 data management, discrete math sort of setup, but it doesn't happen a whole lot. So, for example, if I wanted to count powers of 5, let's say. Now, let's do powers of 3 because there'll be more examples. So, every third number brings me a factor of 3. Okay, so that gives me 10 factors of 3 right there. But you might say, what about that 9 there? It's got an extra factor of 3 you didn't count. You're right. Every 9th term gives me another 3. And then let's use purple. What about that 27? Every 3 to the 3, so every 27th term gives me another 1. And so in total we've got 14. 14 factors of 3. We can use some different colors now that I've got things written out for 5s. Every 5th term. 1, 2, 3, 4, 5, 6. 6 factors of 5. And then, how about blue? That 25 gives us one other one. So, for a total of 7 factors of 5. And if you're curious about it, the factors of 2, well, there's going to be a lot of them, and I think this might be a bit of a waste if you're trying to figure this out, because you're going to be doing so much counting. You're going to get 15 of these, and that's not even considering the fact that you're going to also have to say, well, what about the multiples of 4? Every 4th number also gives me another 1. And then, oh yeah, every 8th one gives me 1. Okay, and then every 16th one. Thankfully, we're not over 32, because then we'd have to be dealing with every 32nd one. Okay, so where are these numbers here coming from, and how could I create some sort of a formula? And then we'll finish off the question. So if you want to, you can skip to the end, and I will... Actually, let's answer the question, and then you can stick around if you want to. So... we've got 14 powers of 3. So 2 to the x is at most 14. Let x equal 7. And we're going to be all set. And 2 to the y, or 2y is going to be at most 7. Well, y has to be an integer, so we've got to have y is 3. And so x plus y is going to be 10. So the most 36s that go into 30 factorial is going to be 7, and the most 25s that go into 30 factorial are 3. There's 3 of them. Okay. Out of curiosity, are these numbers too big for my calculator? Well, that's interesting. My calculator doesn't have factorial on it. Cool. I'll have to remember that for the future. But, yeah, I think this is 30 factorial is way too big for a display on your calculator. Okay. Now, in general, the number of factors of p in n factorial is the following sum, and I'm going to use the floor function. So this is the greatest integer less than or equal to. So it's going to be n over p. Every pth number contributes a factor. Every p squared number gives you an additional factor. Every p cubed term gives you another one, and so on. Okay? Up until, well, basically you could stop, if you knew logarithms, you could stop with something like this using another floor function. But basically you stop when they start hitting zeros, is all you really need to know. So, for example, when I wanted to compute those powers of 5, we'd do 30 over 5, and then 30 over 25. Now this first one here is going to be 6, and 125 goes into 30. So this is, if I can do this on my calculator, 30 divided by 25 is 1.2. That would round down to 1. And that's where we get the 6 and the 1. So for the factors of 2, which I never counted, incidentally, we'd have 30 over 2, 30 over 4. You just keep going until you run out. Another simple way to do it is till you get more than n, really. So 30 over 8, 30 over 16. You don't need 30 over 32, but I'm going to include it so we can point out it's 0. 30 over 32 is less than 1, so that is 0. There's 1 here. There's 3, because 24, but the next one with 32. How many multiples of 4? 7 go into 30, it's 28, and 15 here. Okay. Roughly, to get the next number, you roughly would sort of divide by p, but of course it doesn't always work. 15 divided by 2 is not 7, things like that. But you get 15 plus 7 is 22, plus 3 is 25, plus 1 is 26. So there are 26 factors of 2 there. So just interesting things to note, and it's a formula that is useful. It only works for primes, because say we wanted to do powers of, or multiples of 6. 30 over 6, and then 30 over 36 is too big. So you'd get 5 plus 0, and we'd be thinking, oh, 30 factorial, we'd get 36 to the, what's the biggest, even though you'd get 2 of them here, by our reasoning. Because x would, x would have to be, 2x would have to be less than or equal to 5, so that would be 2 here. And we get 25 to the 7. Incidentally, is 9 an option? 9 is not an option. Okay, but this is what you would think, but what's happening here is you're counting every 6th number, and you're missing the things like a 2 here and a 3 here, just fill things in, can also make a 6. That's why it has to be primes. Always has to be primes. Okay? Now, did I actually say what the answer was? It's 10, but that's A, right? A. So we'll actually write that down. And then we'll move on ahead just so I don't get lost when I start the next video for question number 23. And we'll be looking at that next time. So thank you guys for watching. Feel free to like or subscribe just to show your support. Feel free to like if you learned a new formula that you can use. Factorials, again, as I say, they don't pop up as much as they used to, but you can get a good Hypatia question that uses factorials even without having to define factorials and things like that. So it's a useful sort of counting formula to be aware of. Okay, so I'm glad I could share that with some of you. But up next will be question number 23. Until then, take care.